Okay, everyone, this is section 7.6. In this final section of chapter 7, our goal here is to be able to solve exponential and logarithmic equations. So a little bit of vocabulary. Exponential equations are equations in which variable expressions occur as exponents. So we're trying to solve for some kind of exponent. The property of equality for exponential equations: if b is a positive number other than 1, then that base b of x equals base b to the y if and only if x equals y. So for example, if 3 to the x equals 3 to the 5th power, since we both have the same base of 3 and they're set equal to one another, then x has to be 5. So in example 1, we're going to try to solve for x. Okay, well, 1/2 and 4 can be rewritten. Excuse me. So let's just rewrite them 4 and 1/2 using the same kind of base. And a common base for both of these can be 2, because 2 squared is 4, and 1/2 is the same thing as 2 to the negative 1. And it still has the exponent x minus 3. So now we have them kind of in the same base, but we can do one more thing to them to kind of really set it in stone. So if I distribute the x to the 2 and the x minus 3 to negative 1, I got 2 to the 2x, and then base 2, and if I distribute negative 1 to both of these, negative x plus 3. Okay, so now we definitely have two bases of 2's, and from that property of equality for exponential equations, okay, basically we can ignore the bases of 2 and set the exponents equal to one another. So if I take the exponents out, I got 2x equals negative x plus 3. And if I solve for x, well, I can add this x to the left-hand side. So I'll get 3x equals 3. And if I divide by 3, x will be 1. In example 2, we can do the same kind of thing, but I can't write 4 and 11 using the same kind of base. So what I can do is try to eliminate that 4 with the same logarithm. So I can use log base 4 of 4x is equal to log base 4 of 11. And again, logarithm of a base with the same big base just cancel each other out. So I'm going to be left with x equals log base 4 of 11. And we can evaluate that using the change of base formula. So log of 11 over log of 4. We can approximate that by doing this in the calculator. So alpha y equals log 11 over log 4. It's about 1.729. For the exponent. Some more vocabulary. A logarithmic equation uses logarithms of variable expressions and its corresponding property. If base b, x, and y are positive numbers and b does not equal 1, then log base b of x equals log base b of y if and only if x equals y. If log base 2 of x equals log base 2 of 7, then x still has to be 7. In example 3, I got to solve log base 5 of 4x minus 7 equals log base 5 of x plus 5. Okay, so I got to get rid of their logarithm first. I can't move anything inside the parentheses quite yet because of that logarithm on the outside. So how I can eliminate those logarithms really fast is using the same kind of base. So raise them to both the same base, which is 5's. So those log base 5's of whatever's in parentheses now become exponents, and that log base 5 and the base of 5 on each side cancel each other out. So we're going to be left with 4x minus 7 equals x plus 5, which is an equation that we can now solve. So in this case, I can move my x over by subtracting. So I'll get 3x minus 7 equals 5. And then if I add the 7 over to the right side with the 5, I got 3x equals 12. And then I could just divide by 3 to where x equals 4. So if you need to get rid of the logarithm really fast, raise it to the same base, and vice versa. If you have that exponent, or not exponent, but base, sorry, that you need to get rid of, raise it to the same corresponding logarithm. And example 4, we're still going to solve, and I can't move anything inside the parentheses yet because it's got that logarithm with base 4 on the outside. So again, we could cancel it out by using its own base. So that they cancel each other out, and we're going to be left with 5x minus 1 equals 3. And if I add getting ahead of myself, hold on. So I forgot to put the base of 4 over here. That's very important. So the left-hand side of the logarithm of base 4 and the big base of 4 that we raised it to over there cancel each other out. And on the right-hand side, if I do the same thing, exponent is now going to be 3 on that 4. So 4 cubed is 64. So I'm left with 5x minus 1 equals 64. Now I can start solving. So plus 1 on both sides. So I got 5x equals 65. Then I can just divide that out there. So x is equal to 13. In our last example here, what is or are the solutions of log of 2x plus log x minus 5 equals 2? So right off the bat, what I can do is, because I have this plus sign in there, that means I can condense it a little bit. They both have the same log, and if that plus sign that was there, that means originally they were multiplied together. So 2x minus 5 has got to be 2. And I'm just going to simplify that logarithm real quick. If I distribute 2x to the x and 2x to the negative 5, I got 2x squared minus 10x still equals 2. Now, I can't really move anything because I got that logarithm on both of that. So what I can do, since the log, just normal old log or the common logarithm, has a base of 10, I can raise both sides with a base of 10 so that normal log or the common logarithm and that base of 10 cancel each other out. So I'm left with 2x squared minus 10x equals 10 squared, which is 100. And now I can move that 100 to the left-hand side by subtracting it so that it equals 0 on the right-hand side. Okay, now this is just a quadratic that we can factor. So I need to multiply here. But before I can do that, I realize, well, 2, negative 10, and negative 100, they can both be divided by 2. So let's factor out the 2 first. So I'm left with x squared minus 5x minus 50 equals 0. And that makes it easier on my x method. So I need to put negative 50 up top and negative 5 in the bottom. And we're trying to find factors of negative 50 that multiply to make negative 50 and add to make negative 5. Okay, so 5 and negative 10 do work because they multiply to make negative 50 but add to make negative 5. So I got x plus 5 and x minus 10 has got to be 0. But when I split and solve these, I get that x should be negative 5 and x should be 10 when I solve. but let's make sure that these check out. Okay, so let's plug these back in. So the log of 2 times -5 plus log -5 minus 5 has got to be 2 when I check here. Okay, so when I check -5, I get that log of -10 plus log of -10 has got to be 2. So let's try that in the calculator. Log of -10. Okay, and because I get this I, which you might not in the normal school calculator, okay, this I is imaginary, so that means that it's not defined in the real numbers. So I can't use x as -5. So I can't use x is -5. Okay, but let's say you want to check x being 10. I have log of 2 times 10 plus log of 10 minus 5, and it's got to equal 2. So I know that when I simplify this, this is log of 20 plus log of 5, okay, which is, when I put this together, 20 times 5, because that plus sign, is log of 100. So I have a log base 10, because that's the base for the common logarithm. So what base of 10, or what exponent for 10 is 100? Well, that is 2, and 2 does equal 2. So our true answer is x equals 10, and that is letter choice C. So make sure that when you have to factor, that you need to plug in both of the roots or x values to see if they both work, or one might be extraneous.